With this session and the few assignments that follow, we will now wrap up our official study of the periodic table. But as I said last time, we're not completely done talking about that chart. I will keep referring to the table of the elements as we do future lessons. But finishing things up here in Chapter 8, talk a little bit about what fission and fusion are and nuclear changes, benefits and risks. Now, as I said before, this is a lot more complicated than we can cover in just a few days of an introductory level class. Some of these things you'll learn much more about as you get into higher level of science classes. But are we ready to begin our final official set of notes about the periodic table? Here we go. Fission and fusion, two words that sound similar but have completely opposite meanings. Much of this session is definition type stuff. And here you're about to see two types of nuclear reactions, fission and fusion. Now, fission, this is when a larger nucleus splits not exactly into half, but into two smaller ones. And what will happen, remember, the protons are the atomic number. How many protons, such as in uranium, 92, and when that uranium atom splits, undergoes fission, how many protons get left in each new section is going to determine what element the new atoms are. You'll see examples of that in just a bit. Remember though, fission means division, a little rhyme, a little audio clue to help you keep these two situated. Fission means division. This is when the atom splits, again, not necessarily perfectly in half, but into two smaller nuclei, giving us two different atoms. Of course, the other word, fusion. What happens when we fuse two things together? We get one larger object. So two smaller nuclei combine or fuse together to give us a new nucleus, which, because of the change in the number of protons being added together, will give us a new element. And that happens a lot at the sun, which you are about to see. Ready? All right, the picture may be a little fuzzy, but this is uranium with a mass of 235. Uranium, remember, let's do the isotopic notation, just a quick reminder. Uranium 92 is the atomic number, and the mass that we're talking about right here is 235. So we do a little math here, 5 minus 3, 23 minus 19, assuming I did everything correctly, 23 minus 9 actually, 123. So uranium-235, assuming no mistakes, 123 neutrons. Now, as I said a moment ago, the fission doesn't necessarily split the atom perfectly in half. The 92 protons perfectly in half would give us two 46s, and 46 is palladium. But look at the example here. In this case, uranium-235 splits, and notice what we get. Zr is zirconium with a mass of 97 and tellurium with a mass of 137. Well, zirconium, I use the symbol just to save a little space. Zirconium is element number 40, and tellurium is element number 52. So let's add up the atomic numbers. 40 plus 52 is 92, which is the atomic number of uranium, the original atom. Uranium-235, in this case, in this example, becomes zirconium-97 and tellurium-137, and then there are two extra neutrons, as you see in the picture here, and a lot of energy given off. Uranium-235 could also become krypton-91 and barium-142. Well, krypton's atomic number is 36, and barium's atomic number is 56. Well, add up 36 and 56, we get 92, which is the atomic number of uranium. And you see the masses, krypton-91, barium-142, but then with 3 extra neutrons. Because that's a total of 232, and then there are 3 neutrons left over. So instead of 2 here, we would have 3. So these are just a couple of examples of uranium undergoing fission. In more general terms, the nucleus divides into 2 smaller nuclei. Could be right in half, split right down evenly. Could be 2 different results as you see in those examples, zirconium and tellurium, or krypton and barium. This is performed in nuclear reactors. Now, some elements will decay naturally, but uranium will decay in nuclear reactors. Nuclear reactors are very large, very, very large machines that help scientists generate some new atoms. Remember, 1 through 92 are natural. 93 through 118 are created in these nuclear facilities by changing the number of protons in the atoms. Now, fission can release a tremendous amount of energy, which can be very good if used for purposes such as electricity. And we can get an awful lot of electricity from just a relatively small number of atoms, and we could provide that electrical energy at much lower costs throughout a city such as Jacksonville. Now, I won't get political, but I will tell you, though, this is a controversial topic because fission and nuclear energy can also be used as nuclear weapons, very controversial. And that's all I'm going to say about it. I'm not going to get political. But fission divides. Remember, fission means division. Ready? All right, fusion. Fuse two things together. Take a look at what we see here. I'll put the words up first. At the sun, 2 hydrogen atoms. Now, these are 2 different isotopes of hydrogen. This would be, go ahead and write that on here. This says deuterium, which means a total mass of 2. So the isotopic notation, you know what, let me use a color that will show up better here. Atomic number of hydrogen is 1, and if I move that out of the way, we see a proton and a neutron, 2 atomic mass units. This is tritium, TRI means 3. So in this case, still an atomic number of 1, but a mass of 3. Okay. Now, these 2 are coming together to give us, now we have 1 proton coming together to make 2 protons. And remember, the atomic number with 2 means the element is helium. And now we also have 2 neutrons for a total of 4 atomic mass units. So this fusion happens at the sun, where 2 hydrogen atoms combine, fuse together to form a helium atom. And then the helium atom will separate back into 2 hydrogen atoms. Obviously, there's going to be a lot of energy released in this process. And that energy that's released from the fusion and the fission comes through outer space into our atmosphere as something that we call sunlight. Now, we'll study the different kinds of light that come with sunlight later in the year. But all this happens at the sun. So now in more general terms, 2 small nuclei form by coming together into a larger nucleus. It's not always just hydrogen and helium, but in outer space that happens a lot, especially at the sun. The sun and the stars use fusion to give us a lot of energy. Remember, God created the sun and the stars and the moon on day 4. So God created this process to give us the light and the heat and the energy that we need and all living beings need to survive. Hydrogen joins together to form helium at the sun. Now remember, the sun is actually a small star compared to all the other stars. Larger stars fuse together different elements and then give off, with the fission and the fusion process, give us the light that travels so we can see the stars in the sky that look like tiny little specks of light, but again are actually much larger than the sun. They're a whole lot further away. Low-level radiation, and there's a lot of hydrogen available in outer space in the form of water vapor, H2O, and then again, especially in the Earth's atmosphere. So there's a lot of hydrogen available at the sun to fuse into helium, and this process will keep on going and going and going and going until God says we've had enough. So fission and fusion. Fission means division, splitting apart. Fusion means combining together. Ready? All right, what about nuclear energy? Okay. The fission of uranium-235 produces a tremendous amount of energy. Look at this, 2.6 million times more energy than most energy-dense coal of maybe the same amount as the uranium-235 would be. So if harnessed well and used carefully and for nice purposes, we could get a lot of very usable energy. But again, controversial. Same really with coal. We can get a lot of energy from coal, but coal Also very controversial, and then that's all I'm going to say about it. You've heard of Albert Einstein. He has an element named after him, Einsteinium. If I'm remembering correctly, I think it's element 99. Hopefully I'm saying that correctly, but he does have an element named of him. You've heard this equation, E equals mc squared. Now this means if, this is a theory, not really going to happen, but Einstein's theory said if we could turn all mass in the universe into nothing but energy, how much energy would we get? And C, I'm going to write this on here just so you get an idea. C is the speed of light. So that is approximately 3 times 10 to the 8th meters per second in metric terms, or 3 times 10 to the 5th kilometers per second, which is about 186,000 miles per second. That is fast. E equals mc squared says if we could turn mass into energy, how much energy could we get? Again, it's a theory. It can't really happen. However, in nuclear decay, some of the mass, those protons and neutrons, becomes energy. Not a whole lot, but some does, and that's where we get that nuclear radiation from. Einstein's equation, C is the speed of light, approximately 3 times 10 to the 8th meters per second. So we take the mass of an object in kilograms, multiply by the square of the speed of light. Theory says that's approximately how much energy we could get. And we'll do some practice problems with that very soon. Ready? Can radiation be useful? Well, if you ever had to have an X-ray, as most athletes at one time or another do, we can see that certain kinds of radiation have very good uses, especially in the medical field. Imaging, X-rays for bones. At one time or another, all, if not most athletes, if not all, are going to need some kind of an X-ray. And X-rays can be used for bones, or they can be used to see other parts of the body as well. Now, CT scans will check for organs. I've had both. I've had X-rays on bones and X-rays on my digestive system. I've told you about the little problems I have, and that's why I kind of burp a lot. But a lot of that got discovered by using X-rays and other forms of useful radiation. In nuclear medicine, these can be used to kill cancerous cells and organs. Cells that turn into cancer and then reproduce, that is very dangerous, and as we've all heard, so certain types of radiation, such as gamma rays, can be concentrated on very, very small areas to try to kill those cancerous cells in the organs and try to help cure people from cancer or at least prolong life. There's a device called a radio tracer. That is a 3-dimensional PET scan that will show 3-dimensional images of things inside the body on screens, so physicians trained to read those can see what the problems may be and come up with remedies or solutions, or at least some kind of a treatment. Brain scans use these things called radio tracers. So in the medical field, we have very good uses of radiation. Even with imaging, I could have put on there, the dentist will use X-rays for teeth to see if you have cavities. In security, such as at airports or other places where they have to check your bags, X-rays of your luggage can help identify what may be in the bag. There may be something dangerous that people are trying to sneak through. We can also tell if there are people being hidden in trucks, etc. And using security, X-rays can help find potentially dangerous materials. All right. So we do have some really useful purposes of certain kinds of radiation. Ready? What about the effects of radiation? Sometimes, though, radiation can be a pretty bad thing. Now, you go to the dentist and you notice they put a lead vest on when they have to take X-rays of your teeth. The dental hygienist will do that because he or she is being exposed to X-ray radiation all day, every day, and those can be very dangerous over time. So they'll put the lead vests on us to protect us immediately, and they'll go back behind another screen, and to cut down on their exposure, they'll take the X-rays from a different part of the room that's kind of sheltered off, or even in the room next door. And that's because strong ultraviolet rays and X-rays can cause atoms to lose electrons. That's a process called ionization radiation. And those electrons can damage the cells because electrons carry a lot of energy. And those can cause certain kinds of cancers because damaged cells become rebellious to the body, and when they reproduce, that's what turns into tumors. So prolonged exposure to the highest levels of ultraviolet rays and X-rays can eventually lead to these cancerous cells. That's why you want to protect your skin when you go out in the sun a lot during the summer, because high levels of ultraviolet radiation can cause skin cancers. Radio waves, microwaves, visible light, these are radiation that are less dangerous. Now, cell phones in recent years are much safer than they used to be when cell phones first came out, because those phones would give off higher levels of radiation and higher frequencies of these radio waves and microwaves. Now, holding that thing up to your ear all the time. Nowadays, we text a lot more and hold the phone a little bit away from our heads. And they're also made much more safely, so it's not quite as bad as it used to be. Now, visible light, we'll talk a lot about visible light. There's actually more invisible light, but those are later chapters in the year. Visible light, these are less dangerous, but still can carry some potentially harmful radiation. So be careful exposed to the sun outside a lot. Now, gamma rays, we've mentioned this before, these things can kill instantly. God put the ozone layer in our atmosphere to block almost all the gamma rays from reaching the earth. Unfortunately, some of the harmful UV rays, X-rays, and gamma rays can occasionally sneak through, but gamma rays can be useful if controlled very well in hospitals. We mentioned killing cancer cells, and also sterilizing surgical equipment to kill all the germs and make it safer to use those tools during surgery. So there can be some useful purposes of radiation, but as you see on the screen, we could have some potentially hazardous effects of radiation. Ready? A few more effects. Something called somatic damage. This is radiation that harms our non-reproductive cells, and in that case, at least we cannot pass this harm on to our children through reproduction. That's called somatic damage. Unfortunately, though, there does exist genetic damage. If your reproductive cells are harmed, then this can pass on to your children. So you want to make sure if you have any problems, when you have children, get them tested, make sure they stay healthy, and get treated early if necessary, because unfortunately this does happen. Somatic damage, non-reproductive, does not pass on to children. Genetic damage harms reproductive cells and can pass on to children. Ready? Because we're almost done here. How can we detect radiation? Well, here are three common devices. There are others, but here are three commonly used devices that may help scientists detect radiation. A Geiger counter detects the ionized rays in which the atoms may have lost or even gained some electrons to become ions. And this happens because of electric current. So Geiger counters will measure electric activity, and if there's a little too much, the Geiger counter is going to let you know. And then the scientists trained to deal with that will know what to do. There's a device called an alpha survey meter that will detect alpha particles, 2 protons and 2 neutrons, and may be able to even tell what kind of radiation and therefore get the proper protections and treatments. But that's called an alpha survey meter. One more, and we're pretty much done. And one called the dosimeter. And we have our ID badges. Well, a dosimeter, people who work potentially around nuclear facilities or X-ray machines or places where they may be exposed to radiation, they'll wear these badges that will show how much they might be exposed. Maybe a change of color on the badge, but some kind of identification to show that exposure may have happened, and then these people can get the proper protection and the proper treatment. So these are three very commonly used devices that will help scientists detect radiation: Geiger counter, alpha survey meter, and dosimeter. Ready? And I know you've been waiting to see this. We are done with chapter 8. You have been exposed to learning, And officially, that's our last set of notes about the periodic table. But again, we will continue to mention elements as the lessons come up that refer to those periodic table of the elements. All right, hope you enjoyed it. We'll see you next time.